So, now let us take an example of rotation viscometer. This instrument is used to measure the viscosity of a fluid. So, here, what we do, we place a cylinder inside a rotating fluid, and then that cylinder is hanging from a torsion thread. So, what happens, the rotating fluid will try to turn this cylinder, and at steady state, means after some time, what will happen, this fluid will rotate it, and this, due to torsion, there will be a restoring torque, and the torsion, the angle it turned, so that torsion torque will balance the torque due to the viscous drag of the rotating fluid. So, this is the way in which the rotation viscometer works. Let us see how mathematically we will calculate the torque. So, this is, so torque acting on a cylinder placed in a rotating liquid. So, we will measure this thing, and this torque actually gives that torque is measured, and that gives the coefficient of viscosity of this. So, now we have a cylinder here, and this cylinder has a radius, suppose A, and this cylinder is connected by a torsion string, so that when I rotate it, then this string will we will get a torsion here, and there will be a restoring torque. So, now you see, this is placed inside a cylinder. We can consider this as a bigger cylinder of outer radius B. So, we have a bigger cylinder of outer radius B, and there is a fluid inside it. So, in between the two cylinders, we have a fluid. Now, we are continuously given this omega to the outer drum. So, we have given continuous omega to the outer drum. So, what happens? The liquid in between these two cylinders will begin to rotate, and it will transfer some viscous force to this inner drum, and so the inner drum will get turned like this. So, it will get a force like this. So, due to torsion, there will be a restoring torque, and so there will be a balance. So, the restoring torque will be the measure of how much this rotating fluid applies torque on this. So, let us calculate that torque, and then we can see by observing that torque, how we can calculate the coefficient of the viscosity. This is what is the principle of the rotation viscometer. So, here I neglect that there is a fluid in below this, so that this area is also contact with fluid. So, the area is only curved surface area. So, now consider a cylinder of radius A and length L at rest, placed coaxial with a cylinder of radius B such that B is greater than A and of the same length. Let there be a Newtonian fluid. Let there be a Newtonian fluid between the two cylinders. Important point, the curved surface area of the inner cylinder which is at rest, is weighted by the liquid, not its circular area. Otherwise, we have to also calculate the area of the viscous torques here. In practice, this is also there and we used to calculate this. Presently, we are interested in calculating the viscous drag, the torque due to viscous forces acting from the curved surface area. So, now let us draw its top view. So, we will draw the top view. Now, let us draw the top view. This is the outer cylinder and this is the inner cylinder which is at rest. So, this is at rest and it has a radius of A and it has a radius of B. This is A and B. Inside the liquid is at rest, the liquid is filled and it is in motion. So, the liquid very near to is at rest and very near to it is moving with a constant angular velocity. This has a constant angular velocity omega. So, you see as you go away inside, the omega decreases to 0. So, I want to know how omega changes. So, now I will consider different layers. So, this is the layer and this is another layer. So, this layer has a radius r and this is dr. So, these layers will apply a tangential stresses on this, the forces on this layers. So, we will calculate these forces, this will apply on this will apply on this and ultimately when it is moving, it will try to move this in this direction and there will be a net torque acting on it. So, we will calculate the net torque acting on this. So, now let us see what is the tangential force it applies here. Or so, the tangential force applied by, suppose here I say that it has an omega angular velocity and suppose this is omega naught outer one. So, you see the omega changes. So, here if it is omega inside, here omega plus d omega will be there. So, the tangential force experienced by the cylinder of radius r will be equal to, so let us see not tangential force but stress, tangential stress that will be given by minus eta dv by dr. So, how radially the velocity will change, the linear velocity, but I have been given omega. So, I must relate this tangent, this velocity gradient with omega. So, now you see here the tangential stress applied by cylinder of radius r, that is tau, will be minus eta, that is here dv by dr. So, let us see what is dv by dr. So, now calculation of this velocity gradient. So, now we will calculate velocity gradient. Now, we have v is equal to r omega. So, we have dv by dr as r d omega by dr plus this is omega into differentiation of r, that is 1. So, now you see the total, what is this dv by dr? This is the velocity gradient. Now what I mean to say, that this omega does not actually contribute to the velocity gradient. Only this is the only term which contributes for the velocity gradient. Let us see why. Now you see, if we have constant omega, suppose you see these are different fluid layers, at R n. So they have, suppose, the same omega, So although they have same omega, so at one time one is here and one is, so this is P1 point here, Q1 here, and since they have constant omega, this have a point P2 here, Q2 here. So although they have traversed different distances, they have different linear velocity, but there is no velocity gradient, there is no stresses involved. You see, let us see why this omega does not actually contribute to the velocity gradient. So I have considered two particles with the same omega. Initially this P1 was in and Q1 was there. Now this is the second position, P2 and Q2. So they have same omega, and you can see that there is no stresses in between Q1 and Q2. So they are moving as a unit. So although they have different velocity, that is dV by dr is there, but there is no stresses. So omega does not actually contribute to the velocity gradient. So here I will write dV by dr as only r d omega by dr, because omega, as seen from this logic, that it does not contribute to the velocity gradient. So now let us calculate this quantity. So we see that this V is equal to r omega. So dV by dr as r d omega by dr plus omega, this is not contributed, so only this we will take. So minus eta r d omega by dr. So this is the stress. Now the total force, total torque acting on the cylinder of radius r. So in order to calculate torque, I require force into perpendicular distance, the force into perpendicular distance r, and that force is eta dV by dr into the area of curved surface area into r, that is minus eta, area means 2 pi r into L, this again r means r square dV by dr. So we have torque, total torque equal to minus 2 pi eta L r square, dV by dr we will put this as r d omega by dr. So it will become r cube d omega by dr. So this is the torque that will vary with r. So if I say that the torque T acting is minus 2 pi eta L r cube d omega by dr. So let us integrate this. So this T, this total torque T, and this, if I put this dr by r cube, I will get is equal to minus 2 pi eta L d omega. So you see, when the torque is everywhere the same, because there is no acceleration of this system, the omega is constant. So this r is initially, when r is equal to a, omega is 0, when r is equal to b, omega is omega naught. So we have T 1 by r cube, that is minus T by R to the power, this is minus 3. So, this is minus 2, we have minus 2T to the power A by B, and this is minus 2 pi eta L omega naught. So, let us do the integration. So, now let us do the integration. We will put B here. So, minus 2T is here. This is 1 by R square. So, 1 by B square minus 1 by A square is equal to minus 2 pi eta L omega naught. This minus minus cancel. So, the torque experienced here will be equal to, so here you see the integration means 2 will be this side, not this side. So, T by 2 we will have. So, torque will be equal to 4 pi eta L omega naught A square B square by A square minus B square. So, now you see here I got this A square minus B square. So, this B is large. So, I got some negative. So, here the force I have assumed that this force is actually this this force I have taken negative, but for this torque it will be positive. So, I should not take this negative. So, I should eliminate this negative, and so here if I eliminate this negative, so there will be one negative left out here, and so I will get B square minus A square. So, this will be the torque. We should take care of the negative sign, and so the torque acting which this fluid medium will be applying a torque in this. So, this torque is balanced by the torsion. So, we measure this torque, and so thus we can measure eta as this torque B square minus A square. This is not tension, this is the torque, by 4 pi L, that is omega naught A square B square. So, this is how we can calculate eta. Now, sometimes in the very beginning I said that the cylinders are in contact with their curved surface area, but not with the bottom. But if they are in contact with the bottom, then that will also cause a torque. Let us calculate the torque due to the bottom area. Now, let us see, suppose this is the cylindrical part and this is the bottom. So, what I do, what else we require? So, we have already seen that if this is there. Now, you see here this cylinder is at rest. So, this is at rest and this outer one is. So, what additional thing I require? This T, that is the width. So, we require the width, that is the width of the clearance between the bases of the cylinders. So, now you see what we do, we consider a small portion, this portion which is in the form of a ring. So, you see here the velocity profile, the liquid is flowing here. So, you see I am just drawing this clearance. So, let us magnify this clearance. So, I just magnify this clearance. So, this part and this part, this is the stationary part. So, you see this is the velocity profile. So, the velocity will be different. So, this is the center, suppose this is the center of this, and at a distance, suppose I have a small area here, this area which is at a distance of small r. So, this velocity will be tangential and it will be r omega. And now you see this is the velocity profile that will be linearly decreasing. You can see this. So, this is the circular part and this is the velocity profile. So, we have to calculate that within this region what is the torque. So, let us calculate d torque, and in order to calculate d torque we have to first calculate the tangential stress. So, consider a annular region of radius r and radial width dr. So, this is the annular region, that is the shaded part. So, now the tangential stress is given as minus eta times dV by dy. So, this is r omega, the velocity is r omega and the clearance is suppose small t, the clearance between these two. So, this is the tangential stress. So, force dF will be the area, that is minus r omega by t. So, no need of writing again minus, because I know this is a restoring force. So, this area will be 2 pi r into dr. So, this is dF. So, d tau, that is the torque, will be equal to 2 pi eta omega by t, this r square dr. Now, if I integrate this, I will get the total restoring torque. So, this total torque will be equal to 2 pi eta omega by t, that is r square dr integration from 0 to r. So, we will have 2 pi eta omega clearance t r cube by 3. So, this is the contribution of the torque. So, if we have the bottom also flooded with the liquid, then this much torque will come from this area, and from the curved surface area we have seen what torque will comes. So, the total torque will be sum of these and the previous, and that will be given by, will be equal to the torque produced by the torsion which is measured. So, once I measured that torque, then eta can be evaluated. This is the basic principle of the rotation viscometer.